I'm going to start by recapping some ideas that you should already know. The first one is that current is the rate of flow of charge. So this is electrical current, not current in a stream. And so that means that the formula is that current equals charge over time. The charge that passes in a certain time. And in symbols, that's I equals Q over T. And we can also say that the unit, and in units, and I quite often like to put units in red, so let's see if we can, and 1 ampere, or amp as it's nearly always called, is 1 coulomb per second. So in abbreviations, 1 amp, that's a 1 by the way, not an L, is 1 coulomb per second. So the coulomb is the unit of charge. The second we know is already the unit of time, and the amp is the unit of current. While we're talking about amps, we must visit the current rule. So I've got the green pen, here it comes, current rule. Now the thing that was discovered pretty quickly about current is that current is not used up. So if you've got a current coming along like this, and even if you've got something in it like a battery, let's stick a battery in the circuit. Ooh, something here, stick a battery in here. Okay, here's a battery. Or a light bulb. The current stays the same all the way along the line because there are no junctions. So if we've got, say, 1.2 amps here, then we've got 1.2 amps here, and we've got 1.2 amps there. However, if you have got a junction, let me show the junction with the blob, and put quite simply, it's easiest to look at this with an example, that if you've got 2.4 amps coming along here, and 1.6 amps goes that way, then 0.8 amps must go this way. Now, at the moment, we don't know how to work out whether it's going to be 1.6 and 0.8 or 2.4 or what, but this is a very fundamental rule that the current into a junction equals the current out of a junction in total. So in this particular example, I've only got one current coming in, it's 2.4 amps, but I've got two currents coming out. So 1.6 plus 0.8 must equal to 2.4. So that's the first bit of recap. And then what about voltage? Voltage is the energy given to each charge. What should we put? Gained or lost, I think. So that means that in symbols, first of all, voltage is the total energy delivered over the amount of charge required to deliver it. So then in symbols, the voltage is the energy delivered over the charge required to deliver it. We'd better look at the units next. Well, and 1 volt equals 1 joule, energy is measured in joules, per coulomb. Charge is measured in coulombs, so that in abbreviations 1 volt equals 1 joule per coulomb. I've got a little extra note here for voltage, and that is that voltage is also known as potential difference. But potential difference is a very long phrase, potential difference. So believe it or not, you see that abbreviated to PD. So if you ever see somebody saying, what's the PD across the resistor, they just mean the voltage. And finally, we also have the voltage rule. Now, I said that as far as current was concerned, current was never used up. You could divide at a junction, but it's never used up. It's the volts that are used up. So what we've got is again best shown by an example, because it's quite hard to explain this. But if we've got a source of voltage and we've got maybe two light bulbs here, they're not necessarily the same. They don't have to be the same for this rule to work. But if the voltage of the supply is, say, 1.2 volts, if there are 0.8 volts dropped across this one, then the other 0.4 volts must be dropped across that one. And what's more, if you've got another circuit here, then for this light bulb, the total voltage must be dropped across the single light bulb. Let's consider what's going on with the charge. Charges come out of the positive terminal and they come round, and some of them go this way and some of them go straight on. So I'm drawing little arrows. 1.2 volts means that each charge arriving at the first light bulb here has got 1.2 joules to spend, so to speak. But not all the energy gets lost straight away, because there are two light bulbs in that leg of the circuit. So by the time the charges get, should we talk about X and Y, as they arrive at Y, then they've spent all their energy, so then they go back for more. Light bulbs that come round this route, charges that come round this route, going from X to Y, they also have 1.2 joules for every coulomb, and they have to spend all 1.2 joules in the very first light bulb, because there aren't any others. So what we would say is that in this case, the voltage across the battery is 1.2 volts. The voltage across XY is 1.2 volts. And in the middle route, that voltage is shared between two light bulbs. And in the lower route, all of that voltage is across the single light bulb. We should just have another thing in blue at this juncture, that NB, the voltage across the cell, is known as something very peculiar. It's known as the EMF. Now, EMF stands for electromotive force. The trouble is, it's not a force. So that's why we always abbreviate it to EMF, because if we say electromotive force, you'll tell me, well, it must be measured in newtons. So what's the difference between an EMF and a voltage? Well, the EMF is a voltage, but it's always a voltage gain. So maybe I should have popped that in there, voltage gain. So you never talk about the EMF across a light bulb. It's only the EMF across a battery or cell or a power supply or something. And one final NB. With current, we've got a similar sort of ridiculous thing, and that is the conventional current. I mentioned this earlier, but it goes from plus to minus. But don't tell anybody, but the electrons actually go the other way.